Welcome everybody for this last seminar in the PI series organized by the PhD school. Today we have the opportunity to listen Xavier Alameda-Pineda, and I'll give the token to Elisa that she will introduce him in a proper way.
Okay, thank you, Marco. So it is a pleasure to have Xavier Alameda-Pineda, Javi, with us. He's a research scientist at IRIA in France, in Grenoble, and is working in the perception group. He got his master in mathematics in 2008 and in telecommunication in 2009 from Barcelona Tech, and his PhD in Grenoble. And he was a postdoc in Trento several years ago, but now he's working at IRIA, as I said before, in the perception group. Xavi is an active member of SIGMM, the International Association for Multimedia, a senior member of IEEE and a member of ELLIS. He is currently the coordinator of the H2020 project, SPRING, Socially Pertinent Robots in Gerontological Healthcare. This is a huge project by European Commission with more than 8 million funding, and Xavi is the leader and the coordinator of this project. So today, Xavi, we will talk about socially intelligent robots, and in particular results that he got in the SPRING project and in other projects such as the NRML3RI project and MIIA project. Thank you, Xavi.
Thanks, Elisa and Marco, for the introduction. You made it sound that I was in Trento lots of years ago, and I feel old when I hear that. It was only 5 to 7 years ago, so it's a lot or a few, but you know, depending on what you want to say, you can use one of these. Anyway, so thanks for the invitation. It's a pleasure for me to be here today. As you said, I'm going to discuss preliminary results of these 3 projects, and I gave this title Towards Socially Intelligent Robots, and maybe among these 4 words, the first one is the most important, towards, because I think this is a very long road that we have to pave together with many people. So I'll be presenting a few things that we have done that can help paving this road in this direction. First things first, as you said, I'm in the perception team, and these are the people that are actively participating in this team. So we have a few engineers, project manager, and administrative assistants, and of course, a few or several, depends, PhD students with whom we work every day to make all the things that you are going to see in the slides possible. What we want to do in the team is to effectively deploy a robot in these environments. So this means a robot that is able to navigate in these socially complex environments to address a person or a group of people, to offer assistance or help, to understand the needs of people, to understand if they want to interact or not with the robot, if they are looking for someone, if they need to go somewhere, well, and all these kind of situations that you can imagine. So basically, the robot needs to be able to look, listen, learn, move, and speak in a way that it is socially acceptable. And what we are trying to do in the team is to develop and propose machine learning-based solutions. This is a very broad term that address these specific challenges that you can see in the slide. So what I'm going to discuss today, as Elisa said, is the preliminary results that we obtained thanks mainly to 3 different funding sources. The first one and most important one is the H2020 project Spring, which I am coordinating, as Lisa said, and whose objective is to develop advanced socially assistive robots that are well accepted by all people. You will have, of course, a web page of the projects here, so you can visit them. The MII is not, it's a project that I am taking part in. So this is a very huge project. It's a multidisciplinary institute of artificial intelligence. And within this institute, I am co-chairing the topic of the visual machine perception and interaction for companion robots. And there are several other topics. This is to say that there are many people involved in this institute. And then finally, the MLRI project, or ML3RI project, which is a project that is funded in the scope of the Young Researchers Call of the French funding agency, which is called ANR. You have the ANR here. And this MLRI stands for Multimodal, Multi-Person, Low-Level Learning for Robot Interactions. You can visit the webpage here, and I take just 2 seconds of advertisement. If you go to the webpage and you add details at the end, you will have all the information of a series of seminars that I'm organizing that is called The Devil is in the Details, and where we try to discuss the problems, the engineering problems that are behind some scientific problems. So it's once a month, they are recorded, so you have the links on YouTube, and you can watch them if one of the topics is of your interest. So you can see from the previous slide, which was our, let's say, scientific ambition of the team, and all these projects that are funded for us, is that we are interested in multi-person scenarios. So this means that a robot interacting with many people, and then how the robot perceives the scenario and how the robot should interact with the scenario. Now, in this talk, I will mainly focus on the perception part. Since the interaction part started not so long ago, and also with the impact of the pandemics, we have travels running experiments. So now we will probably start having this opportunity, but it has not been the case in the recent past. So the way I'm going to organize this talk is that I'll present, let's say, contributions that have been presented either at a conference or in a journal, and every time I'll put forward the title and the people that have participated to these contributions. So the first one is about multi-object tracking or multi-person tracking. So in multi-person scenarios, of course, you need to know the position of the various people. And this is work, of course, from the perception team, but also from Alyosha and Laura that are in Technical University of Munich, and Newton, that is a former member of our team and that is now in the Distributed Robotics Lab in MIT. And this paper was presented at CVPR last year. So multiple object tracking, I think it speaks by itself, is the problem of tracking. So basically inferring the position of people over time, and doing so of many people. So you can see here in an image, every different color is one person, and you can see at the bottom of the bounding box a series of squares which represent the position of the very same person in the previous frames. Okay, so the idea is to follow all these people when they walk here in the street, but it could be an indoor environment or whatever. So traditionally, the way multiple object trackers were trained, but deep multiple object trackers were trained, they would input RGB images, and the deep multi-object trackers were supposed to output bounding box coordinates. Then these bounding box coordinates were assigned optimally with the Hungarian algorithm to the ground truth bounding boxes that you have on the top. Okay, and once you have the assignment, you can compute the L2 loss between the ground truth and the bounding box and the infer bounding box and backpropagate. So this is what you do at training. And then at testing time or evaluation time, you compare these, the infer bounding boxes to the ground truth, and you run the standard MOTA metrics that I'll present in a while. So what we did is we basically replaced the Hungarian algorithm by a deep Hungarian network that we call DHN. And this deep Hungarian network is a way to approximate the optimal assignment of the Hungarian algorithm. But the nice part of this is that this approximation is now differential. All right. So basically now I can and then we also approximated the MOT metrics by MOT losses. The differential now. So basically now we have a proxy of the MOT metrics with whom we are training our deep multi-object tracker. So basically now everything is differentiable. So we backpropagate from the MOT loss into the deep multi-object tracker instead of backpropagating from an L2 loss. So as I said, the standard practice is to, so basically you have the tracking results on the left. Each of them corresponds to one row of this distance matrix, and the distance is computed between the inferred bounding boxes and the ground truth bounding boxes that you have here, OT1 to OT capital F. All right, so each row corresponds to an inferred bounding box, and each column to a ground truth bounding box. So this is a distance matrix. We will discuss later about which kind of distance we use. Right now, let's think that it's a distance matrix. And then the Hungarian algorithm, as I said before, computes the optimal assignment given this distance. All right. The problem is that this has no analytical form, and of course, it's not differentiable. So what we did, and this is what we'll explain in the next, we approximated this with the deep Hungarian network. And then, once again, in standard practice, at test time, well, at train time, we compute the L2 distance, got that. But at test time, we compute these two metrics, which are basically the multiple object tracking accuracy for MOTA, and MOTP is the same as with precision. So in tracking, you can have 3 types of errors. So false positive is detecting someone that wasn't there. False negatives is missing someone that was there in the image. And identity switches is when you are tracking 2 people, and then these people may get close together in the image space, and then the tracking may switch the bounding boxes. Okay, so this, you keep on tracking both persons, but you switch the identity. All right. So basically, MOTA is 100% if you do not make any of these mistakes, and then for any of the mistakes, then you subtract. Okay, and it can go actually to minus 100% if you do things really, really bad. And then MOTP, is the precision. So it's the distance error for those assignments that are correct. All right. So this gives you an idea of how good are, in terms of localization, are the correct assignments. So the problem is that neither the Hungarian algorithm nor these metrics here are differentiable with respect to your detections. And we try to address this issue by proposing first the deep Hungarian net that approximated the Hungarian algorithm. So the input of the deep Hungarian net must be the distance matrix, and the output that you see here in pink should be an approximation of the optimal assignment matrix. A good approximation if possible, of course. Now, there are a few things to take into account when we design this deep Hungarian net. First is that the number of tracked objects and the number of ground truth objects is different from one time frame to the next one. So basically, N and M that you can see here, the number of rows and columns, changes over time. So basically, I have to have an architecture that accepts inputs of different sizes. And the second one is that the Hungarian algorithm, which is what we are trying to approximate, is a global optimization procedure. So therefore, the output of the Deep Hungarian network must have a global receptive field. So each output neuron of my DHN, of all this architecture that we will go in detail now, has to have the entire input as receptive field. Okay. Otherwise, we will not be able to approximate a global optimization process. So how do we do that? Well, we basically have this architecture here that has flattening on the row direction, then sequence-to-sequence bidirectional RNN. We reshape to flatten in the other direction, so column-wise, to have another bidirectional RNN, and then to reshape and basically apply pixel or entry-wise FC layers that are responsible for computing this soft assignment matrix that must approximate the optimal assignment matrix. So now we are done with the first part, which is approximating the Hungarian algorithm, but we also have to approximate the losses, the metrics, sorry, which are the MOTA and MOTP. So basically, you have to compute the false positives, the false negatives, identity switches, and so forth and so on. So to do that, we basically input, we run the Hungarian net. Here you can see it in orange yellow. This gives us a soft assignment matrix. And then what we do is we add this column of a certain threshold delta, and then we do row-wise softness. So basically what happens here, you can see it, you can see that in the first row, when we apply row-wise of max, the third entry is value 1, okay, is in green. So we are assigning the first row to the third column. So the first track to the third ground truth object, right? Something similar happens in the second row with the second column. But when we apply this to the third row, well, the highest value is on this extra column that we have added, which means that we should not assign this track to any of the ground truth entries. Okay, so basically this track would be a false positive. We detected an extra person. Okay, so if we sum over this yellow column, we have an estimate of the expected number of false positives in this frame. We can do the same with adding a row, and this will account or have an estimate of the expected number of false negative. And if we have the previous assignment here, we can apply this max. We can apply a mask to have an estimate of the expected number of identity switches. All right. Of course, with this assignment mask on the top, we can multiply this by the distance matrix, and this gives us a proxy for the MOTP. All right, which was the procedure. So now we have everything we want, and everything is differentiable. So basically, using these two approximations, the Deep Hungarian network and the MOT losses, we are able to train this deep multi-object tracker. Everything is differentiable here. So we are training with a proxy of the MOTA metrics. So at the time when the best method for tracking was Tractor, and we put this DeepMOT on top of Tractor, and we have observed both in Mod 16 and Mod 17 that it basically increases the performance, especially the MOTA, because it can reduce the identity switches, and sometimes it can reduce also the false negatives. So overall, this was a very nice solution, especially because you can use DeepMOT for whatever deep tracker that you have. So one word about the distance matrix So basically, which kind of distance are we computing? So if you can see in the image on the top, if we use the intersection over union, something that is very common in bounding boxes, we have a problem. It's because the bounding box in green, which would be, you can think of it as, a bad inference, so the tracker here is not very well trained, and it infers this bounding box. And the intersection over union, when compared to the blue bounding box number 1 or the blue bounding box number 2, both intersection over union are 0. Okay, so it doesn't matter how do you move the green bounding box around a little bit, right? This is still going to be 0, and therefore the gradient is 0 here. And this is very problematic because if the network has an inference that is really incorrect, it will not be able to learn if you use the intersection over union. So an alternative is to use the L2 distance. But the L2 distance doesn't give you anything about the size of the bounding box, only the distance between the centers. So what we concluded is that we needed to use something between the two. So basically we have this L2 norm with the exponential, but it's virtually the same, and a combination of this L2 norm and the intersection over union, as you can see here on the upper right part of the slide. And the second thing is that this, even using this combination of L2 and intersection over union, this is purely geometric. So if you are equally far from two bounding boxes, you don't know what to do. So what we did here is we added something that relates to the content of the bounding boxes. So it's some sort of an appearance model. We are basically having a ReID head, and then with this ReID head, we compare the ground truth appearance to the predicted appearance using the cosine distance. And we add this on top of what we had before, so we are able to, even if geometrically we are equally far from two bounding boxes, we can say it's either the first one or the second one with the visual content. Now, this is a very interesting problem that is called actually person re-identification, right? And this is useful for tracking, but the problem per se goes far beyond tracking, actually. So on top of using it to determine if a bounding box should be to the left or to the right of two candidates that are geometrically equally far or close, the ReID branch can also be used to reactivate tracks that we put to sleep because, I don't know, maybe someone went out of the field of view. So now we're going to have more information about this person. And then whenever someone new is entering the field of view, we say, okay, did I see this person already or not? So we can reactivate the track. And we thought about investigating something that is that we could quickly summarize as unsupervised adaptation for person re-identification. And we did this with Guillaume, Yihong, Radu, and myself from the perception team, and Stéphane, who is in Telecom Paris in Paris. And this was presented earlier this year at ICPI. So for those who don't know person re-identification, so standard or supervised person re-identification is, okay, you have a bunch of images that are taken from different cameras for which you know the identity label. So this is John, this is Mary, and so forth and so on. And now you get a new image, and you have to compare this image to a gallery, which is another set of images that has the same identities, and you pick out basically the identity that is close in appearance, right? And you say, okay, this person is Mary. So in this supervised ReID problem, you have ID annotations everywhere, okay? I mean, this is good for research, but in practical applications, you don't know, in many applications, you don't know who your robot or your camera will be looking at, right? So then the question is, if I now have a data set a target data set T with no ID labels, can I adapt or change something in the model that I have trained in supervised manner to adapt it to the target data set, and how to do that? So there are some works in unsupervised person re-ID that were not necessarily tackling the domain adaptation issue, and they are based on clustering and fine-tuning. Okay? So what does this mean is you pre-train your source, and then you alternate between running a clustering on the target data set. This gives you observer labels, and then you use these observer labels to fine-tune your feature extractor file. Okay. So of course, I said something wrong at the beginning. Of course, these both SSG and MMT are for unsupervised domain adaptation in person re-ID. Okay, just to be clear on that. So basically, they cluster, they extract features, they cluster them, and then they use these observer labels to fine-tune the same feature extractor that was just used to extract the features, and they loop on that. And we have basically adapted this with a different structure. So what we propose is to do adversarial domain adaptation on top of all this. All right. So basically, we have a feature extractor here, and then this feature extractor has is in phase of two classifiers. One is an adversarial domain discriminator, which is trying to guess if your image here comes from the source or the target datasets, and an ID classifier that is either using the labels of the source dataset or the observer labels of the target dataset. So the problem with this is that we can have negative transfer in the sense that our discriminator can actually learn identity-related features instead of domain-related features. And why is this? Well, this is very easy to understand. The problem is that we do not have the same identities in both domains. So these are usually data sets that are recorded in different conditions. So John will be in domain number 1 and not in domain number 2, and Peter will be the other way around, right? So if we learn identity features, we can of course guess the domain very, very easily. And this is what we refer to as negative transfer. So we observe this phenomenon, and we propose something to alleviate that. First of all, we propose that instead of having a discriminator on the domain, we could have a discriminator on the camera, right? So basically, now my discriminator here is trying to guess which camera was this image taken from. But we still have negative transfer problem. And the reason is that the identities do not appear with uniform probability in all the cameras, right? So to address this problem, we basically condition the camera discriminator with the centroid of the cluster this image belongs to, okay? And this is the way we have to tackle the negative transfer phenomenon, and we call this conditional camera adversarial training. So the advantage is that, of course, we can plug this in any clustering and fine-tuning strategy. So we plugged it in CAN-U, so in MMT, and we call this CAN-U MMT, and in SSG and CAN-U. So CAN-U stands for camera adversarial network for unsupervised, and then what follows, right? So when we evaluated this, we used, of course, standard ReID datasets and standard ReID ReID metrics. So this is the results are shown in this slide. And so naturally, we compare SSG to CAN-U SSG and MMT to CAN-U MMT in 4 different settings. And we can see that overall, we systematically increase the performance. So it can be like in the first table is like 3% on rank 1. In the second table is sensibly more, which has some value because MSMT is kind of a huge data set. So the results are really nice from a ReID perspective. So the next work I would like to present is about monocular 3D pose estimation. So of course, when you have these robotic scenarios, you want to know where people are and who are they, if you have seen them before, but also, how are they oriented and why not, why are they doing? And to answer this question on what are they doing, of course, the pose is very useful. This is work that was done in collaboration with, of course, my PhD student, Juan, and Enrique and Francesc from Institut de Robòtica Industrial in Barcelona. And we presented this again early this year. So what we wanted to investigate is, there are all these works, right, doing monocular 3D pose estimation, and they address this as a single person scenario. So basically, the pose of each person is inferred independently of the pose of the persons around. And we wondered if, we could use the pose of the person in the environment, of the other persons in the environment, to increase the performance of existing monocular 3D pose estimation methods. So the intuition is, all right, I have, let us assume that the bounding box is provided, that's not our problem right now, and I have a method to extract the 3D pose for the red person, the person with the red bounding box. But now I know what's the pose of the person in the blue and in the green bounding boxes. And then this PyNet, this pose interaction network, is supposed to refine the red pose into something else because I know the pose of the people around. So basically, we use the standard Mascar CNN for the detection, and then PoseNet, which is an existing method in the literature for pose estimation. And then we have our PyNet here, which is basically a bidirectional RNN together with some self-attention and a few FC layers. And at training time, of course, we are supervising the refinement of the 3 poses. And we can basically train this network with all permutation of P1, P2, P3 possible. So this allows us to augment a lot of the data. Then at test time, we just refine, let's say, the first entry. So we have to run this 3 times if we want to refine 3 poses. And this works better than actually running everything the same way at training and at test time. So for training, we use the MUCO composited data that you can see on the left, and for testing, the MUPOT3 data that you can see on the right. So the data set on the left is basically using poses of people that were taken independently, and then putting them together for training. And we can see, if we pay attention to the details, that we can actually refine the poses of the people. So you can see in black you have the ground truth, in red you have the output of PoseNet, and in green you have the output of PoseNet plus our method. So basically we are able to improve a little bit over the state of the art. And we have tried also to add the network capacity to corresponding to PyNet on top of PoseNet, and this does not provide good results. So basically, the improvement of this comes really from the fact that the network is taking a look to all the poses to refine the original pose. So you have here detailed results per sequence with the 3D PCK metric and on average. So basically, we beat the state of the art in all the sequences except for one in this data set. So we were quite excited. The problem is that these scenarios are scenarios that are, let's say, social interactions. So you have seen, so basically people here are discussing. And of course, there is some correlation and some, basically there is some information between the poses, but this information we believe is limited. So we decided to record a dataset that is called the Extreme Pose Interaction Dataset. And we recorded a series of actors performing acrobatics in the Kinovis room that is here at INRIA. And they were performing different acrobatics. So I think we have something like 17 different actions that are performed by 2 different couples. Every action is performed 5 times. And you can see from the results that they are very, very diverse in terms of movement and in terms of interaction between the two people. Okay, so then we moved. This will appear soon, hopefully at ICCV. We will see. Anyway, the data will be released, I guess, sooner than later. We then moved back to social interaction, again in multi-person scenarios. And what we wanted to do here is to train a network to generate a sequence of social actions of a group of, let's say, 3-4 people that are interacting together. Okay. This is the main idea and was done with Louis and Dominique, that are both colleagues here in Grenoble. And this is submitted at IEEE Transactions on Effective Computing, but it is already available in archive if you are interested. So these are the kind of scenarios that we have. So you can see that people are mingling here in a, whatever, in a bar or in a room. We don't know exactly what this is. And basically for each person, you have the action that is being taken. So hand gesture, drinking, speaking, and so forth and so on. And then, so this is the match and mingle data set. It was published a couple of years ago, 3 years ago already. And what we want actually to learn is the dynamics of the people involved in the interaction. Right? So the idea is we observe part of the interaction, so the actions of the 3 people over a certain period of time. We give this to our social interaction GAN, and then the social interaction GAN is supposed to output a sequence of actions that make sense with respect to what was observed, but also that the dynamics make sense with respect to what would be a natural interaction. So here, all this generation is on action tokens, right? We are not generating video, just to make it clear. It was a first step to see if we could capture actually the dynamics of the interactions. So this works with, of course, a sequential generator and 2 sequential discriminators. So we have what we call a dual stream discriminator. The first discriminator here on the upper right is what we call the individual stream, because it's evaluating if each of the generated sequences, the orange, the red, and the blue, makes sense on its own, is realistic on its own. And then you have an interaction stream, which is checking if the orange, red, and blue sequence of generated actions makes sense as an ensemble, makes sense together. All right? So, and we need these 2 discriminators. This is very important. We need that each sequence is realistic on its own, but also that the 3 are realistic together. Also, we used something that we call the local RMN, which is basically having a discriminator that is evaluating every subsequence of delta t tokens instead of a discriminator that is evaluating all the sequence at once. And this strategy here below works better. And I'm saying this because I think that it's important that this kind of engineering tricks, are known and widespread, because at some point you may need something like this. And if you have heard that talk, then you say, okay, at least I could try, or I could go to the paper. So if you ever have troubles with discriminating sequences of things, maybe a discriminator that is taking a look to windows of these subsequences of this long sequence would be a way to address this issue.
Question?
Yes?
Just a curiosity. So why this architecture is better than the others? I mean, is there a rationale behind this decomposition that?
Well, so basically here with the LSTM you can do two things. So either you take a look to the final hidden state of the LSTM, which should accumulate all the information, but it is very sparse input, so it's tough. Or you take a look to all the hidden states of the LSTM, and these may actually be too dense. So what happens here is that you can take a look to this. So basically you are, and then, it's like locally, you're taking a look if this makes sense or not. So if something doesn't make sense, you're immediately penalizing this part, right? So I think that this could be a bit more, it's a bit more easy to identify the part of the sequence that doesn't make sense.
Okay.
All right, so now going back to our problem of interaction generation, one of the difficulties that we faced is how to evaluate that. So generally speaking, GANs or adversarial strategies are difficult to evaluate. But in our case, we could not even use the Frechet inception distance. The reason is that when you generate images, you use VGG16 pre-trained on whatever to extract these features that we use for the FID. But we had token sequences, so we could not use VGG to extract features. So what we did, and this is what it's explained in the second paragraph, is that we trained a network on an auxiliary task. And this task was to estimate the proportion of ejection in the sequence. So that has nothing to do with what we want to do, but it uses the same data. And then once we have this network pre-trained, we can extract features from our sequences and then compute what we called sequence Frechet inception distance. So this is what you have here in the results, together with the marginal entropy and the conditional entropy. That should be actually the highest or the closest to the data the best, while the SFID is the lowest the best. And we have many more experiments in the paper, but here it's just a summary. We had the simple, dense, and local RNNs with and without supervision, and either attempting to generate 40 frames or 80 frames. And in all these situations, what we are proposing was better overall, at least in terms of marginal entropy, conditional entropy, and SFID. So you can see that here, you can see from the results that actually the local discriminator is really important. I wanted also to show the training curves, just for you to understand that it's not only that the final performance of this local discriminator is better, but it's also that it converts faster, which actually might be a little bit linked. But anyway, I mean, we trained these models for far more epochs and to 20,000, and often they didn't reach the same performance that the local RMN reached in like 3,000 epochs. So it really made a difference. All right. So until now, I talked a lot of what are people and what are people doing. It is also important to understand what are people saying. We are not going to discuss speech recognition. Previous to speech recognition, in noisy environments, one needs to enhance the speech signal, or basically clean the speech signal from the noise. So what we are going to discuss now is, so the main actor here is Mostafa, which is a researcher at UNC, and it's also collaboration with Laurent and Radu. And this was presented at a journal, and then at ICAST last year, and really presented this year as well. We are focusing in audiovisual speech enhancement. So basically, we assume that we have some noisy speech signal. You can see here a spectrogram, a noisy spectrogram on the bottom left. We also have the video of the person that is speaking, and more concretely the mouth region. And the aim is here to output an enhanced speech signal that should have less noise. All right, so it's a clean speech signal idea. So some people address this in the literature as in a supervised framework. What I mean by this is that they, as you can see in the figure, they input the video frames and the noisy speech, and they want to output the enhanced speech. The problem with this is that you are basically learning to denoise, and if the properties of the noise change at test time, as we will actually see, then your network does not perform very well. Okay, because you have not seen this kind of noise, so you think that part of it is speech, or you don't understand that part of the speech is actually speech, and you put it as noise, and so forth and so on. So what we aim, because in robotic scenarios we don't know. I mean, maybe we can pre-train for some kind of noise, but we don't know. We cannot know all the kinds of noise that we will encounter. So we went for an unsupervised strategy in which we train our model only with clean data, and then the noise distribution is trained at test time together. So at the same time as we are enhancing the speech signal, right? I'll try to explain how this is possible. To do that, so we started with very simple strategies based on VAE. So we have audio only VAE. We input audio, we output audio in the VAE. We have a video only. Basically, we try to infer the clean speech signal from the lip movements, which is a bit hard. And then the first thing we proposed is to concatenate audio and video, both in the encoder and in the decoder, to fuse auditory and visual data when training the variation autoencoder. So just a little technical riddle here. I didn't put many equations in the slides, but from time to time a wild one appears. If you train this network directly, as it is, because the input audio and the output audio are exactly the same, which is a clean speech signal, the network has no reason to use the visual data. Because of course it can reconstruct almost perfectly the audio from the audio. So what we had to do is to give some reconstruction power to the visual prior. So this is what is written here in orange. This is a reconstruction loss, but when you are sampling the latent code Z from the prior that depends on the vision, okay? As opposed to the posterior, which is the standard thing to do, the posterior that depends on the audio and vision in our case, all right? So this orange part here is basically giving some reconstruction power to the vision prior, and therefore it's forcing the network to learn and to exploit the visual data. The problem with this architecture, which is the AVVAE, is that we are systematically using audio and video, even if at some point audio or video can be heavily corrupted. So we proposed another architecture, which we call, it's kind of a mixture of VAEs, And at every time frame, we can decide to sample either from the video prior or from the audio prior, right? The ones that you have seen in this slide here. So we sample either from this architecture, the first one, the audio only, or the video only, right? So this is interesting because it's done in an unsupervised manner. Well, we will skip the technical details. We can go through them later if you're really interested. And what is important is that then your posterior distribution is also a mixture. So basically you have two encoders, an audio-only encoder and a vision-only encoder, and you are selecting from which of these two encoders are you sampling. And once again, you are selecting this in an unsupervised manner. So we just set the model, right? We are not saying at every frame if it should be video only or audio only. So this is very nice. So we have 4 different architectures: audio only, video only, the concatenation, and the mixture. And this is only for clean signals. And now what we assume is that at test time we will have some noise, Bn. This noise will follow a non-negative matrix factorization-based model. Once again, let's skip the details. So we had to develop a variation REM algorithm that would jointly allow to jointly estimate, the clean speech signal from noise observation. So this is the speech estimate, as well as the noise parameters, which are the non-negative matrices, W and H, right? So this summary that is, one slide here, in equations on a paper may be like something like 5 pages. And this is why I'm concentrating on this in only one slide and avoiding you all the pain. But just to say that it requires some mathematical derivations to reach to a computationally tractable solution. Now, when we evaluate this, so we did that in the standard anti-CVTV dataset, many speakers, many hours of speech, a training and a test, different kinds and levels of noise, and then 3 performance measures, which are the SDR, objective measure, and 2 perceptual measures. And you can see here on the slide the improvement over the input, all right? So why am I saying this? Because when you plot improvement curves over the input in the speech enhancement, you have something that is bell-shaped. Why? Because when the input is very corrupted, you have minus 15 dBs, it's very difficult to have a huge improvement. When the input is very good, it's very clean, it's also very difficult to have a very good improvement. So usually you have this kind of bell-shaped curve. You can see here that the blue curve is doing this, let's say, almost monotically increasing. This is the audio-based BOE. So obviously, when the audio is very bad, it's doing very hard, and when the audio is very good, it's doing very good. The vision-based BOE has almost the opposite tendency, which is also very logical. And then among the various strategies, you can see that the green one kind of outstands globally from the rest, and this is the mixture that we have proposed, one of the 2 versions, not going to the details. If you want to hear samples of clean speech, you can go to these web pages, so clean in-ear perception research, blah, 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 and the same with the other web, ABVAS, all right? I hope that I will be able to upload the slides or to make them receive the slides so that you have all these links. And you can maybe take a look to the slides a bit more calmly. The issue of this mixture, even if it performs very well, the issue is that actually with all these models, is that they process frames independently. So basically, if I shuffle my signal and video frames with the same permutation, I will obtain the same result, which is a bit weird because we know that the speech signal, of course, has some temporal dependencies and some consistency. So basically, we propose, and this is our this year's ICAS paper, to extend the mixture with Markovian dependencies. So now I'm going to have my mixture variable that has some Markovian dependence, like an HMM. This will help me generate the latent code, and both together will help me generate the S. Okay, so this is my generative model, and then with the noise, I will obtain the noisy speech, of course, right? So basically, on top of what we discussed last time, now my mixture variable that is here in this yellow circle has some Markovian dependencies. All right. So we call this switching VAE because you can interpret this as an HMM that is switching between different VAE-based emission probability. And we compared our switching VAE with our mean VAE in clean signals, in clean visual signals, I mean, and in noisy visual signals. And you can see that our switching variation of encoder is actually outperforming the mean VAE, except when there is a lot of auditory noise. But for all the other cases, in the three measures, PESC, SDR, and STOI, we are outperforming the mixture that is done independently at each time frame, which actually makes a lot of sense because when you have some kind of visual perturbation, let's say you put your hand in front of the mouth, this lasts for a certain window of time and then it stops, right? So there is some kind of temporal consistency, and this is where the HMM is playing the interesting role. But this is not enough in terms of temporal modeling, and I will go quickly through that because we are running out of time. We presented some sort of review and applications of what we call actually dynamical variation encoders. So this is joint work with Laurence, Simon, which is in Rennes, Xavier, which is in the team, and Julien and Thomas that are colleagues here in the room. And just to give you, let's say, an overview of that. So you probably know probabilistic models like Gaussian mixture models and their, let's say, sequence counterpart, which are state space models like the Kalman filter. Of course, you know deep and CNN networks and their sequence counterpart, which are RNNs. And then there are the VAE, which are basically deep probabilistic models, and one can wonder what are their sequence counterparts. So are they deep state space models, probabilistic RNNs, or sequential VAEs? So basically, it's the three of them. And we call them dynamic variation autoencoders. And an example of these things is what we published at ICAST last year, which is a recurrent variation autoencoder, which is very similar to standard VAE. Okay, you have Z is the latent code and X is the observation. It's just that now Z goes first, so it's the input of a recurrency, HT, that will be sent to the next timestamp. Okay, so in some sense, the latent code is accumulated over time. So in terms of probabilistic dependencies, it means that ZT minus 1 will have an impact not only on XT minus 1, as in a VAE, but also in XT, in XT plus 1, XT plus 2, and so forth and so on. Okay? So you can see here that compared to a VAE or even to the switching variation autoencoder, the dependencies that we have are much more long-term than in previous cases. And at inference time, so the encoder has the drawback, if we can say that way, that the posterior distribution depends on future observations. So now it actually becomes quite messy because the temporal, the probabilistic dependencies are getting a bit wild, so you have to take a lot of care when you are analyzing the structure of your posterior distribution. And up to a point that for some models that were published before and that lie within this general umbrella of dynamical variation autoencoders, in the original papers, they proposed a certain generative model. For instance, here Storm has these probabilistic dependencies. And when they they proposed the inference model, they forgot about all the errors that you can see here in yellow. All right? So some of them are justified to have causal processing, like online processing, but some of them not. So in SRNN is a different kind of dynamical VAE, and they actually respected the true structure of the posterior. But for instance, for a third one, which is called VRMN, once more, they did not respect the exact structure of the posterior. In this case, even if they did not explain this as clear as I will formulate it now, so in this case, I think they ignored the future, the non-causal dependencies, so that they could have online processing even at inference time. So all these and many, many, many more things are explained in this review paper. It is called Dynamic Variation of Encoders. A review, a comprehensive review. And you have also all these models implemented in PyTorch. You can see all the information in this web page. And we have presented already results in 2 applications, which is speech analysis resynthesis and speech enhancement. So we believe that this is a class of models that is very, very interesting. And we encourage you strongly to take a look to this web page. So now to conclude, well, we are, as you can see, focused on the study of multi-person interactive scenarios. We have proposed methods that try to address some of the challenges that you can see here, like localized detect and track, re-identification, the cross effects of interaction between what people are doing and what's their pose, how to fuse auditor and visual data, of course, unsupervised adaptation to new domains. With these latest contributions with the switching VAE and the dynamical visual encoders, how to account for sequential information. And then finally, and this is one sentence, but as some of you might know, represents months of work, is how to implement solutions that are computationally tractable in platforms such as the ARI robot that you can see here on the slide, that it's the one that we are using for the Spring project. And this actually takes really, really a lot of time, and it's often overlooked when we present scientific contributions because the engineering details are a bit boring, but they cost a lot of time, effort, and therefore money. So thanks a lot for your attention, and I'm very happy to take questions of the contributions that I have described, or even more general questions if you have them.
Thank you, Xavier. It was very, very interesting. Somebody has a question?
Yes, I have actually.
Okay.
Thank you for the presentation, Xavier. So I have basically 2 questions. One is about the tracker, and the other is about the social interaction GAN. So for the tracker part, if the final aim regarding human-robot interaction, if the final aim is regarding human-robot interaction, I wonder whether you tested this tracker on egocentric videos. If so, can you elaborate a little bit on this? What were the challenges where the pipeline is more failing, etc., etc.?
All right. So I don't think we have. All right. So as I said, we were trying on the results. You can see here tractor, and then which was something that existed already, and then and then we trained tractor with DeepMOT. Then since then there is something else that has appeared in the literature that's called it's called FairMOT. This is a new tracker that has actually a very high performance on the standard data sets. And this is the one that we are using right now in the kind of scenarios that you are describing. And basically the problems that we have are not, let's say, during short-term tracking. The issues that we have is, when someone went out of the field of view for like 10 seconds and comes back, it's not always easy to re-identify this person. So it's more a re-identification problem than a tracking problem. We might encounter tracking problems if the lighting conditions, for instance, are very different from the ones that you have used during training. So if that's the case, I probably recommend to fine-tune or to retrain your tracker. But if you're in normal lighting conditions, I think that current trackers are more than enough for track, let's say, 10 people in the waiting room. You have to think that in current standard data sets, you have sometimes you have 70 or 100 people in the image, and the trackers are actually quite good at keeping most of the people on track. So it's not about the number of people, it's not about how fast they move, it's mostly about what happens when they go out and they come back 10 seconds or 1 minute later, and their re-identification phase.
Yes, but if the robot is also moving, so assuming that robot is the one who is tracking the people, then sometimes you are maybe observing my full body, but sometimes only my head.
Okay.
Is it a challenge for your tracker or not?
Okay, yes, I understand this. So the answer is yes, because basically all these trackers are person detectors that have been fine-tuned for tracking, basically. So if these have been trained with full body detection, and if you only see my upper body, then it fails. And I verified this last week with my colleague. So most of the time it will fail. Then if what you want is to track upper body, then you have to fine-tune on upper body detection, which is, I don't think technically it's not difficult, because you basically take the bounding boxes, divide them by 2, and then fine-tune with the upper part of the bounding box. And I think this should be the job.
Yeah, I agree. Thank you. So the second question is about the social interaction GAN. So, okay, I think if we are talking about interaction, this means that, let's say I'm interacting with you. So you basically do an action to me and I react to your action. So this is a simple description of the interaction. So in which part of your pipeline you are considering the interpersonal actions? I couldn't capture it.
Yes.
Because to me, it shouldn't be only generating the action per person, but actually maybe it should be the interaction indeed of the people.
Thank you, because I actually forgot to mention that. So it's a very good question. Okay, so you can see here on the left my generator. The generator is first encoding the observed sequence, which are these colorful squares here. It's encoding something into a certain representation, Cn, and then this representation is given to this series of LSTMs. And you can see here that you have, okay, the arrows that go out of the generator, but then the arrows that go into this pooling module, all right? So this pooling module is acting at every triplet of actions that you generate. It's basically taking all of them together, creating a unified representation that is put back again into the LSTMs, all right? So the output of this pooling module is a joint representation of the 3 actions that have just been generated. And this is the way we can take into account the interaction when we are generating.
Okay.
Excellent
Yeah.
question.
Thank you.
Are there any other questions? Oh.
Sorry, this is Marco. But related to this, so are you able also to detect some causal dependency? So, I mean, if I push you and you will push me back and identify whether there is this reaction to one action that has been done before.
So, yeah, just to clarify something, these actions here are basically, I don't know, like scratch head or speaking or breaking. So they are not necessarily actions. They're actually not actions that you do on someone else. It's actions that you do, so they are social actions, all right? So what we observed during, if you take a look, already to the original sequences, okay? So I'm not even talking about the generated sequences, but on, let's say, the ground truth, you can see that the often, not all the time, but often the status of a person changes and there is another change, closely in time, there is another change of another person. So this is something, it's a pattern that is naturally seen in the data. And therefore, the generated sequences also have it. I know it's a bit abstract. I don't want to give any stupid example here, but yeah, one example very clearly, for instance, is that when someone starts speaking, it is most of the times because someone else stopped speaking, or it will make another person stop speaking, right? So this is one pattern. So in the vicinity of a change, you have usually another change.
Okay,
so it's more like conversation environments.
So, I mean, and the speaking is very easy to understand and to see. I mean, sometimes when someone, scratches the head, they will not ring because someone is scratching the head, right? So some of the examples do not make sense. But for the speech case, yeah, it makes a lot of sense.
Okay. And so this information that you can extract, so dependencies and interactions schema, so are then used in some knowledge base and knowledge representation to perform reasoning, high-level reasoning for decision making, or to decide what the robot should do later, or
no, I mean, our aim is that this will provide to the robot some idea, some cues on what to do or what not to do. But we didn't try that yet, just to make it very, very clear. The other thing is that in order to extract some more high-level reasoning or features, we would need this annotation, and we don't have it. So this is we are a bit constrained by the data. This is not a critique because getting all this data is already a huge effort. So, but yes, we are always a bit limited by what was annotated originally in the data, and this, of course, depends on what the authors wanted to do in the first place.
And just another curiosity, what is the typical training time for a task like this?
That stuff. Wait. No, I don't remember. For the quick one, which is this local guy, I think not too much, because even if you see here an incredibly huge number of epochs, you have to think that these are, it's sequences of action tokens, right? So in terms of processing, these networks are not really large. So I think it's kind of easy to train that, provided we have the right parameters. So at the beginning it was difficult because we had few or no intuition on how to, how to set the learning rate, how to set all these things that are kind of important. But I think that the training in itself doesn't take too much. But I don't have a precise figure now.
Okay. Other questions from the audience?
I think we are quite also half an hour after the, but it was very nice, Xavier. You've done a lot of things recently.
I try.
I was not updated on all of them.
Yeah, we can discuss whenever you want. Yeah.
No, I mean, I was updated on the tracker ones, but on the other, not. But it's very interesting.
So, if there are no other questions, so let me thank again Xavier for having this nice presentation to us. And let me just remind that this is the last seminar in this series, and in September we will start with a new one. And we are hoping for having some more, even more interesting like this one talks in the forthcoming series.
Thanks for the invitation, guys.
Ciao. Thank you.
Thank you. Bye-bye, Xavier.